Hello everyone. So previously we were done with this one, solving 50 problems on the this one graphs topic, right? So code forces problems we solved actually. So from today, let's start this one, solving LLD problems. So this is going to be the huge this thing as well. So this is going to be huge as well. So we'll be solving 50 important problems that might be asked in the interviews or that you have to know, right? So we'll be solving around 50 very important this one. What do we call LLD problems? Yeah. The first one, uh, the first one, let's see here what we are asked to do here, right? So here we are asked to design and implement a thread safe rate limiter. Here, here we have been asked to design a rate limiter in simple terms, right? We have to design and implement a thread safe rate limiter that restricts the number of incoming requests per user. What it does, that restricts the number of incoming requests per user or key within the given window or key within the given time window. Sorry. Yeah, this is fine, I believe. Now, the first step, let's discuss the functional and non-functional requirements. Yeah. So here, first, let's discuss on the this one functional requirements as said, right? So we have to allow or reject incoming requests per key, right? It may be for the user, service, API key based on the configured rate limits. Yep. So this is the first thing. Next, we have to support configuring. When I say we have to support configuring, so we have to go with a max request and window seconds. So what we need to go with here basically, so we have to go with max requests as well as plus this one. What do we call window seconds? Yeah, we have to go with a window seconds. Yeah, we have to go with a max request and window seconds per key, right? It may be either global or per key override. Yep. So next, let's move on with the next one. So we have to go with the accurate enforcement of the configured limit. Yeah. So we have to go with the accurate enforcement of the configured limit. At most maximum requests allowed in any rolling window of window seconds. Yep. So let's move on with the fourth one. We have to provide an allow request of the key. We have to provide an allow request of the key API that returns true, right? So that returns true, nothing but in the case if it is true, then it is allowed. If it is false, then rejected, or false, nothing but the rejected. We have to support querying usage statistics, right? So this is optional basically. This is optional. So we have to support querying usage statistics in the sense, so we have to go with the current count in the window. Then we have to consider the time to earliest expiry. Time to earliest expiry. The final one is related to the latency, nothing but low latency decision. Why low latency decision here? So this is suitable for the high throughput. Whenever we have the low latency, this one, it's suitable for the high throughput, right? So we'll be going with the, basically we have to go with the low latency decision, right? So this is about the functional requirements. Let's collect the, or let's get the non-functional requirements as well. So non-functional requirements here, this one, the first one is performance. Performance, basically the decision must be big of one here, right? The decision must be big of one amortized per request, right? Basically expecting the DQ operations, right? So decision must be big of one amortized here per request. Next, let's move on with the scalability part. Yeah, let's move on with the scalability part. So when I say scalability, so it should be, or we should be able to scale horizontally meaning, so we have to provide the support, this one, we have to support or support the Redis or other distributed stores, right? So it has to support Redis or other distributed stores. Next, we have to keep in mind about the thread safety as well, right? Thread safety or the concurrency part. So when I say thread safety or the concurrency, it must be safe under concurrent requests from multiple threads or the processes. Again, so it must be safe under concurrent requests from the multiple threads or the processes. Next, let's discuss about the memory as well. When I say memory, we have to keep the memory bounded by the bounded per key actually. When I say we have to keep the memory bounded per key, we have to evict the old timestamps. Just remember this, we have to evict mean we have to remove, right? So we have to evict old timestamps. Yep. For extremely high cardinality, we have to support TTL or the eviction. TTL or the eviction or the removal, right? So this is fine. The fifth one is availability. What is meant by availability here? Basically, what does it do here? See, rate limiter should be highly available. Yeah, rate limiter should be quite obviously highly available. So basically, whatever the design that we go with, design should support Redis backend distributed mode. Yeah, Redis backend distributed mode. So this is it for the availability part. So next comes the consistency. When I say consistency, for the single node in memory, so for the single node in the memory, so we have to go with a strong consistency. Yep. So for distributed store, considering the Redis basically, eventual or the near consistency based on the chosen algorithm, whatever the algorithm that we choose actually. This is fine. Now let's move on with the this one. The third part basically, what do we call? Algorithm choice decision. Yeah. So what's the choice of the algorithm that we'll be going with here? So basically, so let's go with this one chosen algorithm part here. So we will be choosing sliding window log. So we'll be going with a sliding window log here, right? So we'll be going with a sliding window log. Yep. So this is the algorithm that we'll be making use of to solve this particular problem. Yep. So again, here we'll be going with a sliding window log. Basically, in simple terms, we'll be making use of the DQ of the timestamps per key, right? So this is fine. So how it works basically, sliding window log, we have to know how it works primarily, right? So how it works, for each key, we will keep record of the timestamps for particular, for each key, right? Uh, we will keep the record of the timestamps when the request arrived. When the particular request has arrived or requests arrived, so we will keep the record of the timestamps. When a new request arrives, when a new request arrives, we will remove the timestamps older than now minus window seconds. So we'll be going with the now minus window seconds, right? If the number of types, this one timestamps are less than the maximum requests actually, then we will accept and append the current timestamp. Else we will reject. Else we will reject. So what are the pros and cons of choosing the this one sliding window log? The main pro or the advantage actually, main pro or the advantage of this is, so this is precise for the rolling windows actually, right? This will be accurate enforcement. Also, it is simple to reason about. It is simple to reason about. Yeah, this is one of the advantage. And what might be the biggest con here? Mainly memory per request. Memory per request, right? We have to store that timestamp somewhere, right? So mainly here the biggest con is memory per request, meaning storing the timestamps here. So if many requests or many keys are found actually, then memory will quite obviously grow huge, right? Memory will this one quite obviously it will grow huge, right? So that's one of the biggest advantage here. That's one of the biggest advantage here. Just give me a second here. So we were stuck at the last page actually. This is fine, man. Yeah. So basically, DQ of the time, this is fine. Con is main, this one, memory per request, right? So storing the timestamps in simple terms. If many requests or many keys, if we have many requests or many keys are present, then the memory grows huge, right? So this is one of the main cons or the disadvantage part. Yeah. So what are the alternatives to this one actually? What are the alternatives to sliding window log basically? Right, we are going with the DQ of the timestamps per key, right? So what are the alternatives basically? We can just go with a fixed window. When I say fixed window, we can count per window bucket, right? So this is very cheap, big of one, right? But it suffers from the boundary bursts, right? So the second one is we can just go with a sliding window counter. This one, this is approximately, right? So approximately in the sense we can keep two buckets and interpolate. We can just keep the two buckets and then interpolate, right? So this will be of the less memory, approximate correctness. Yep. Or we can just go with a leaky bucket. Leaky bucket, also known as the token bucket. We know this one, right? So this is good for smoothing bursts, but and also supports the refill rate. It also quite obviously leaky bucket algo that basically supports the refill rate as well. Token bucket is good for the burst allowance, right? Then, or we can just go with the Redis plus Lua script, right? Redis plus Lua scripts, right? So for distributed consistent enforcement with the atomicity, we can just make use of the Redis plus Lua scripts, right? So why we have chosen this one actually instead of these things? Why we have chosen sliding window log here? So see, so this is best and balanced for precise behavior and simplicity. Mainly, it is known for the simplicity for the single node demo, right? So that is the reason we will be going with this one sliding window log, right? So mainly we'll be making use of the DQ of the timestamps for the per key actually, right? So next, let's move on with the concurrency and the data model. Yeah. So when I say concurrency and the data model, so for the data model, we will be going with the in-memory single node. For the data model, we will be going with the in-memory single node. Yeah. So we will be making use of in-memory single mode. Yeah. Just give me a second here. 1 second. So as I've said, for the data model, we'll be going with the in-memory single node, not mode, sorry. It's node actually. Yeah. In-memory single node. So we have to consider three things here. One is limits, and another one is store, and another one is locks. When I say limits, I'm speaking of the configuration object. Configuration object in the sense key, we have to consider max requests and the window seconds. Key will be this one. Consider key for the key will be this one considering max requests as well as the window seconds, right? Fallback to the default, fallback to a default. So this is for the limits actually. What is so for the store, what we have to this one what we can consider, as we are as we will be going with a or yeah, as we are going with this one Python, or as we are considering the Python programming language, so let's go with the default dict mapping, right? Default dict mapping for the store actually. When I say default dict mapping, so we are considering key to the this one basically DQ of the timestamps, right? Each DQ holds a recent request, this one, recent request timestamps within the particular window. Then we will be going with the logs, the last one, right? So when I say logs, again, we will be going with a default tick mapping, meaning, so we'll be making use of the key for the threading.log, threading.log, right? So this is fine grained locking per key for the concurrency. This is fine grained locking per key for the concurrency. Yep. So this is it for the data model one. Yeah. Next, let's discuss about the concurrency as well. Yeah. Before writing the code, let's discuss the concurrency as well, concurrency part as well. So when I say concurrency, this one concurrency model, just give me a second here. So when I say concurrency model, so first thing that comes to our mind is in process or the single machine. So when I say in process or the single machine, see, we will be making use of, or we can make use of a per key lock to minimize the contention and make the operations atomic. Yeah. So this is one of the things. The simple terms here is, so just listen to this carefully. The simple things here is, first acquiring the lock for the key, right? Acquiring the lock for the key. Then we can purge old timestamps from the left or DQ, right? So we can just write it in this way, while DQ and DQ of 0 less than or equal to now minus, so whatever we have considered, window seconds, right? So then we can just go with the DQ dot pop left. Yep. So then check the length and append if allowed. Finally release the lock, right? So that's what we can do. So the next step would be this one, y per key locks. So why will be going with the per key locks here? So basically it reduces, or primarily it reduces the lock contention compared to the global lock, right? If keys are skewed, skewed in the sense hotkey. So we also call this one as hotkey, right? If keys are skewed or the hotkey, that key will be actually contended, right? Just consider lock striping or atomic operations in Redis for the hotkeys, right? So this is one of the things. Next, let's go with the distributed mode. When I say distributed mode, nothing but the, it is also known as the multi-node, right? Distributed mode is nothing but the multi-node here. So here in this case, we will use a centralized store that supports atomic ops. Yeah, will be we can just make use of a centralized store here that supports atomic operations or the ops, basically Redis with either two of these things, right? So one is Lua scripts that trim and check length, then append. Yeah, or use sorted set with a timestamp scores that we can do, or we can just go with a token bucket implemented in the Redis with atomic decrement or the increment. Yeah, so this is it for the distributed mode or the multi-node. Yeah, then let's go with the final one, nothing but the memory eviction or the memory removal, right? So memory eviction is nothing but for many ephemeral keys that we are making use of. So we can just go with, or we can just use the background eviction, right? We can just make use of the background eviction or the TTL, right? Or the TTL. In Redis, we can just use TTL, right? So I am speaking of in memory. In memory, we can just make use of the LRU. LRU also known as the least this one least recently used cache, right? Or the periodic cleanup. In Redis, we can just make use of the TTL. In memory, we can just make use of LRU, nothing but the least recently used cache or the periodic cleanup. Yeah. So this is it for the data modeling and the data model and the concurrency model. Yeah. Now let's do one thing. Let's hop up into the main part, nothing but let's see the UML diagram, right? So yeah, let's come to the main part, UML diagram. So this is the main, this one rate limiter class here. So we will be going with a default max, which is of the type int, and we'll be going with a default this one window, which is of the type float actually. And then we will be going with the limits in the sense we'll be going with a dict of key to the max comma w here, max comma w. Then as per the discussion, we will be going with the store and locks, right? Store nothing but the again dict of key to the dq, locks again dict of key to the lock here. So this one you can just look into the diagram here, UML diagram. So this is fine. So then we will be making use of the allow request method, right? Allow request of key basically, which is of the type bool here. So this is nothing but the bool here, right? So if you are not able to see, this is nothing but the type boolean, right? So this is fine. Next, we will be going with the set limit method. So basically, which consists of the key as well as the max as well as the window. If you can't see here, this one is key, max, and window. Yep. The final one is get usage of key. So get usage of key consists of the count as well as the TTL. If you can't see this one, the last one is TTL. Yeah, this is fine, I believe. So what is the sequence that we'll be going with here? So let's discuss the sequence part as well. So client, so this is nothing but the rate limiter dot this one allow request of key, right? So first thing what we'll be going with, acquire the locks, right? Acquire locks of key, right? Locks of key. Then we will purge the old timestamps from the store of key. From where we'll purge old times, this one timestamps actually will purge this one. We will purge actually old timestamps from the store of key, right? So this is fine. Next, if length of store of key, so this one, if it is less than max, then we will append of now. Then we'll be going with what we will append actually. We will append now actually. Nothing but in that case, we will return true, else we will return this one. What do we call? Else return false, right? Then finally, we will be releasing the lock. So this is the sequence that we will be going with basically. Yeah. I hope this is pretty clear, man. Yeah. I hope this is pretty clear. Next, let's do one thing. Now, as we have seen the UML diagram and as we have discussed certain things that we need to know, now let's start writing the code. Yeah. Let's start writing the code. So here, as I've said, we will be going with a sliding window log this one algo, right? So because it is thread safe actually, that is the reason we'll be going with it, right? So let me do one thing. Let me go with import. Let me go with the threading actually. Yep. So this is fine. Next, let me import time. Let me import time. Yeah. Also from collect, we need the default dict as well as the DQ as per the discussion, right? So I'll just go with here collections as well as let me import here. What are the things we need to import? One is default text as well as the DQ, right? So this is fine. So the next step here, we'll be going with a class rate limiter as per the UML diagram, right? So I'll just go with a class here, rate limiter, right? So just look into the UML diagram. Whatever we discussed there, the same thing will be this one articulating here in the form of code. Yep. So first thing, let's go with the constructor part here. Nothing but the init and Python, right? So I'll just go with here. So yeah, a def init. So along with the self, let me go with one thing I need here as default maximum requests, nothing but the type int, and default window seconds. We have discussed this one. Default window seconds, nothing but it is of the type float, right? So I'll just go with default here, this one, window seconds. If you look at the UML diagram, you'll get it, the first one and the second one. Yeah. So now within the constructor part or the initialization part, so first let's continue with the configuration here. So I'll just go with here, this one, default max. Let me type here, man. Default max. So let me assign this one to the int of default max request. So this has to show at least. It's not showing. Okay. So let me copy this one and paste it over here. Right. So this is fine. Default max request. Next, I'll just go with this one, default window. Right. So let me go with the default window here. Default window. Let me assign this one to the. This is of the type float. Right. So I'll just go with a default this one, window seconds. So let me pass this one. So this is fine as well. Now let's go with a per key. Per key in the sense, it may be either user or the API, right? So basically, this one, what do we call DQ of the timestamps? And we know this one, it is monotonic. Yeah, we have discussed this one already. So I'll just go with here, store. Well, let me make use of the default dict here. Yep, default dict of let me pass DQ. Let me pass DQ. Yep, this is fine. Then let me go with locks as well. Let me initialize this one with default dict of, let me pass here. Sorry, we have important threading, right? So this is fine. Threading dot, let me pass lock here. This is fine. Yep, the final one, this is optional as per the discussion. We had discussed this one earlier as well. So this is optional per key overrides actually. Key to max comma window. If you look at the this one rate limiter, this one UML diagram, right? So let's go with the limits actually. So you can just look at the UML diagram. So writing this one, your UML diagram is very important. So whatever we have mentioned that this exact same thing will be articulating in the form of code actually. The exact same thing. So I'll just assign this one. So this is fine. Yep. Now, what shall we do? Next, let's go with a set limit. So let's go with a set limit, get limit, as well as the let's go with a set limit and the get limit first. So let me go with def set limit. So here I need the parameters. One is key. I need max requests here. So this one I can just leave here. Max requests of the type int, and let me go with window seconds here. So let me copy somewhere I have given window seconds, right? So let me copy this one window seconds. Let me paste it over here. Window seconds, which is of the type float actually. This is fine. Yep. So within the set limit helper method, the first thing I'll just go with here. Let me type this one. Limits of key, limits of key. We have to set this one to the int of max request actually. So this has to show. Yeah, max requests along with the this one float of, we have to go with the window seconds. Yeah, yep. So this is fine, man. Now let's move on with the get limit actually. So I'll just go with def. Let me go with get limit here. So within the get limit, I need only one thing, that is nothing but the key, right? So I'll just return here what we need to return. So I'll just go with limits dot get actually. So I'll just go with the key here. Along with the key, let me go with this one, default max here. This has to show. Yeah, let me select this one, default max, as well as the default window, right? So I'll just select here default window. Yeah, default max as well as the default window. Now finally, let's go with the allow request. So why we have to go with the allow request here? So we are just attempting to allow the request for the particular key, right? We are just attempting to allow the request for the key, and we which returns true actually if allowed. If the key is allowed, then it will return true, boolean value true, and it will return false if rate is limited. If the rate is limited, then it will return false. Yeah, this is completely thread safe. Yeah, it uses per key lock. As we had discussed, the per key concept actually, it uses per key lock, per key key lock, right? So again, why we are writing the allow request helper method here? So basically, what it does, what we are doing here, so within the allow request, so we will try to attempt to allow a request for the key. It returns true if allowed, and it returns false if rate is limited, and if it is rate limited actually in simple terms. Yeah, and it is thread safe as well, uses per key lock, right? So let's start writing the helper method allow request. Just give me a second here. Allow request, right? So I just need here key actually. Yep. So let me go with the bool here, nothing but the boolean. So this is fine. So within the helper method allow request, the first thing, let me consider the variable now, and let me go with time dot monotonic. So one second. Yeah, it is showing monotonic. Yep. So this is fine. And also let me go with the max request here. Max request. Along with the max request, let me go with the window seconds as well. So let me go with window second. So here in this case, I'll just go with a self dot. So let me make use of the get limit here. Get limit of the key. Yep. So this is fine, I believe. Yep. The next step, let me assign lock to the locks of key, right? Has to show, yeah, locks of. Yep. So this is fine, man. Now, let me make use of with lock. So with, let me go with a lock actually. With lock, so let me assign q to separate store of, let me pass the key here. Let me pass the key here. So the next thing is, uh, so we have to purge expired timestamps. So which is older than the window, right? So let me consider this one. Uh, Variable boundary. Let me set this one to the, we have already discussed this one, now minus window seconds, right? So I'll just go with the window seconds here. So this is fine. So the next step would be, let me write the simple while condition here, while q and q of 0 here, while q and q of 0, if it is less than or equal to boundary, if it is less than or equal to boundary, then let's do one thing. I'll just go with pop left here, q dot pop left. Yeah, so this is fine, man. Yep. Now let's go with a simple if condition. A simple if condition. So let me write here, if length of queue, this is fine. If it is less than max request, then we have to append the now to the queue as discussed. So this one I'll just go with a queue dot append now. This is fine. Next, we have to return true. So sequence I had shown you within the next to the UML diagram actually, the same thing. We will be returning true here. So this is fine. Else, else what we will do? We will return false. Else return false. So I'll just return false here. Yep. So this is fine, man. Yeah. Now let's do one thing. We are done with the allow request helper method, right? Allow request helper method. Yep. Next, let's do one thing. Let's go with a this one, get usage helper method, man. Yeah. Let's go with a get usage helper method. So what does the get usage helper method do here? So how it is useful for us basically? Yeah. So we will return current count in window along with the time to oldest expiry here, right? If no entries, then we will be returning 0, 0. This is how it will be helpful or useful. Let's start writing the helper method. This one get usage actually. Def. So I'll just go with a usage here. So this is fine. Let me go with the self as well as the key. Yep. So within this helper method or the function get usage, first again, same thing actually. So let me consider this one, these two things. Yeah. So let me copy this one and let me paste it over here. Right. So this is fine. now equals time dot monitor. This one remains same. Max request as well as the window seconds. So we are just assigning this one to the self dot get limit of key. So this remains same. Then lock equals self dot lock dot key. So this one the same thing actually. So let me do one thing. Let me paste it over here. The next step would be with lock. This remains same actually again. So let me copy this one here. So let me paste it over here. So with log, so first what we are doing here, we are going with q equals self dot store of key, right? So the same thing again. Let me paste it over here. So this is fine. Next, after q equals this one self this one, we will set the boundary to this one now minus window seconds, right? So let me copy this one again. Let me paste it over here as well. Again, after that, we are just going with a while of q and q of 0. If it is less than or equal to boundary, we will be going with a q dot pop left, right? So this is fine. And then if length of q, this one, what do we call? If length of q, then what we will do instead of appending from here, we will change actually, right? So let's do one thing. Let me copy till here actually, while till boundary, right? So let me copy the same thing here. So I'll just go with here. Sorry, me paste it over here, right? So if length of, so this one is fine. Then what we are doing here, basically, if length of this one q actually, one second, yeah, mm, q dot pop left, this is fine. If length of q we are going with, right? So here, instead of the length of q, so let me delete this one. So here, if of, so let's write here, if not q, right? If not q, then let's return as per the discussion, what did we discuss actually? We will return current count in window or this one time to oldest expiry, either of the two things. If no entries at all, initially what we will do, we will return 0, 0 here. First, initially we have to return what we have to return here, 0, 0. Yep, this is nothing but the 0, 0.0. This is fine. Next, let me go with oldest equals q of 0. This is fine. Then let's set the TTL to max of 0, 0.0 here. Then oldest plus window seconds. So let me go with the window seconds. This one, window seconds. This is fine. Yep, minus now, minus now. Finally, we have to return something. Let me return uh, count as well as the TTL. Count as well as the TTL, right? So next, what shall we do actually? Next, what shall we do? Let me go with a demo of the concurrent simulation, right? So I'll just get the example usage of the concurrent simulation from the Google, right? So just give me a second. So this is it for the code actually, whatever the code that we have written. So a kind of a demo or the concurrent simulation. Let me consider or let me take that from the Google. Just give me a second here. See, I have just pasted this part actually from here to here. So what we are doing, let me explain you this one. So initially, we are just showing the concurrent simulation. I'm just showing the concurrent simulation here. So we have considered the worker here, limiter, set to rate limiter, key string, attempts at type int, pause float, this one, results in the form of list, and index start, nothing but the index start set to the int. Yeah. So what happens here, what we are doing, each worker makes attempts, each worker makes attempts, request for the key with a pause seconds between the attempts, yeah, and appends the tuple, nothing but the thread index, attempt index allowed to the results, yeah. So here we are just moving on with a for loop for I in the range attempts, for I in the range attempts. So allowed, we are just setting this one to the limiter dot allow request of the key, and results dot append. So we are just going with a threading dot get this one ident, right? So also I allowed limiter as well as the this one limiter dot get usage of key. So we have passed. So thread this one time dot sleep off. We are just pausing this one. We are just passing pause here. This is fine. Now we are going with a very simple example here, which allows 5 requests per 2 seconds per key actually, right? So see here, limiter equals rate limiter. We have called the this one main class here, nothing but the rate limiter. This one, whatever we have written here, this one rate limiter here. So we have just passed this one, what do we call default max request. That is, we have set this one to the 5, and default this one, what do we call default window seconds, we have set this one to the 2. So basically what happens here, so we are allowing 5 requests within 2 seconds. After that, it has to get rejected, right? So we are allowing, how many requests we are allowing here? We are allowing 5 requests here within the 2 seconds, default window seconds, 2 seconds. So after 2 seconds, all the, this one, what do we call request has to get rejected on its own. Yeah, see here, key user, we are just consider this one Alice, right? So I'll just go with a Bharadwaj here. So this is fine. Key user, I'll just go with a Bharadwaj here. Results, we have set this one to the empty initially. So we're just creating 3 set threads here, simulating the concurrent clients for the same key threads. We have set this one for t in the range because we are going with the 3 threads here, creating 3 sets, that is simulating concurrent clients for the same key, right? So I have passed 3 here, this one range actually, and each thread will attempt 4 this one requests spaced at 0.2 seconds. Yeah, we are just going with 0.2 seconds. Yep. Threading.thread, we have made target, we have set this one to the worker, arguments nothing but limiter key 4, and 4 because here we are attempting 4 requests based at this one 0.2 seconds. Yeah, 4.2 results as well as t into 4, right? So this one is we are starting the thread, and thread dot append, we are appending the thr variable. So this is fine for thr and threads, individual thread thread dot join. So this is fine. Finally, we are printing the results on the order of the recording, in the order of recording. So for R in the results, so TID attempt this allowed usage equals R. This is fine. Count TTL equals usage. So finally, we are just printing something for the interactive purpose. See, this is what we are displaying. Actually, we are going with the string interpolation. So we are starting with the F thread. We are passing the TID attempt. So we are passing the attempt here. Allowed. If allowed, else we will get the output rejected. So within the 2 seconds, basically 5 requests we are allowing. After that one, we have to we are going with a keyword rejected, uh, meaning we will not allow the request. We will reject the request after the 2 seconds, right? If allowed, else we are going with the keyword rejected in the window count. Yep. So this is what we are doing. Simple. Yeah. So now, if I run the code, so as we had discussed actually, so let me explain this one once again in very simple terms. Yeah. So this one rate limiter init, what we are doing here. So it sets the default maximum in the window and initializes the store as well as the logs. See here, initializes the store as well as the logs. So if I hover over here, so you can just see here, yeah, default init. So we are initializing store as well as the logs here, right? So allow requests of key, allow requests of key. So this one I'm speaking of allow requests of key. What it does here, allow requests of key, it uses time dot monotonic. So this one time dot monotonic here, right? It uses time dot monotonic for the monotonic timestamps. Yeah, and also it acquires per key log. We have discussed this one already. Also it acquires this one per key log, and it purges the expired timestamps from the left of the DQ, right? And checks the current length versus maximum request. Finally, it appends if allowed and returns the boolean, and returns the boolean. Yep. So this is fine, I believe. Then let's move on with the get usage of the key. So this one actually, this helper method. So what we are doing here basically, this is the helper that returns in window count. That returns in window count. Yeah. So this is fine, I believe. And time to oldest expiry for the debugging or the monitoring, and time to expiry, this one, and time to expiry for the this one debugging or the monitoring, right? So then we are going with a demo part one. So this demo part, just we have discussed this one just now. Let me tell you this one. Basically it spawns three threads here, right? Creating 3 threads, simulating concurrent clients for the same key. So what it does here, it spawns 3 threads making requests concurrently for the same key, for the same particular key. 3 threads are making requests concurrently for the same key here, right? Each thread sleeps 0.2 seconds between attempts. It sleeps 0.2 seconds between the attempts, right? So with the maximum request equals 5 per 2 seconds, we should see some requests allowed, then later rejected until the window slides, as we are going with a window, this one sliding window, right? Sliding window basically. Yep. So now as per the this one, whatever the code that we have written, as per the code, actually, if I run the code, the output that we need to get here is allowed up to 5 requests must be allowed within the time frame of 2 seconds. Then the later request has to be rejected, and the sleep time we have set that one after one request we have set that one to the 0.2 seconds. Yeah. So let's check the same. So let me come here. Let me give Control J. So I'll just give Python followed by the sorry. Uh, 1 second. Let me copy this one. Yeah, let me give here Python again, followed by the file name.py. Yep, so let me hit enter. So we have some error here. Exception in the thread one worker respect. So we have some error here. Let's check what we have done wrong here. Rate limiter object has no attribute, rate limiter get limit. So where is this actually? Line number 24. Just check the line number 24, 24, 24, 24. Yeah, so this is fine, I believe. Just give me a second here. So here, oh yeah, I have given two underscores here. Let me remove this one actually. Self dot get limit of key actually. This is fine. Give clear screen again. Let me run this one now. Again, we have the error. Rate limiter object has no attribute. Get limit get limit. So this one is fine. The line number 24. 1 second. So let me do one thing. Where I have where have I used this one get limit actually? Here get limit. Oh, this one name. Oh yeah. So here also I have to set this one, right? So just give me a second here. Let me set this one. Let me give underscore here. So this is fine. Now let me give clear screen and let me run the same. Still have the same thing. Rate limiter object has no attribute. Yeah, this one also I have to change. Where line number 41, 41, 41. Yeah, this one. Let me remove one underscore. Yeah. So this is fine. Call this one again. Name count is not defined. You mean round? Line number 53. 1 second. So yeah, here count is not defined. You mean round? We haven't defined count here. So where is count? Oh, I have not. So let me do one thing here. After q dot pop left here. So let me do one thing. Um, let me assign the count to this one. Length of q actually. So this is fine. Now this error has to be gone. Let's see. So yeah, now we are getting the correct output. See here, we are getting allowed. So this is fine in window 1, in window 2. So this is also allowed 2, 3. You can just count here 4 as well as the 5. So all other requests are rejected here. So uh, order can be anything here. Order doesn't matter. All the requests are rejected here, and the first 5 this one attempt or the requests are allowed here. Maximum request we have set to the 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 requests are allowed here. And also we are displaying here in window 1, in window 2, in window 3, in window 4, and in window 5 actually. 2 seconds, 2 seconds, 2 seconds. So this one, 1 point, this one, seconds actually, 1.796, 1.796. So this one from here it is rejected from the 6 seconds. And also one more thing. So we have the time gap of 0.2 seconds for each window, right? So we have set that this one as well. We have discussed this one as well. So we are getting the desired output one. We are getting the desired output. So this, whatever the code that we have written for the rate limiter, accordingly with the functional requirements and the non-functional requirements that we have collected, or as discussed actually, this code works absolutely correct, right? So whatever the code that we have written works absolutely correct. Just give me a second here. So one more thing I want to tell you, if you are writing the same code, exact ordering can vary. Yeah, exact ordering can vary. So here you can get allowed at the end, allowed in the middle, anywhere, but you have to get allowed only 5 times. Just remember this one, because we are allowing only 5 requests within the 2 seconds. Yeah, just remember that one. Yeah, exact ordering can vary due to the thread scheduling here, right? Right. Notice just notice one thing here, that once 5 requests exist within the 2 seconds, further requests are rejected until earliest timestamp slides out. Earliest timestamp slides out. Yeah. So we are getting the desired output. Yep. So whatever the code that we have written works absolutely correct. Yep. So this is fine. Now let's do one thing. As we are done with the this one, what do we call, writing the code actually, accordingly with what we had discussed earlier. Now let's discuss the limitations of the current code. Yep. Let's discuss the limitations of the current code. So here, accordingly with what code that we have written actually, first we have to we are considering limitations of the current code, whatever we have written for that one, right? We are considering basically limitations. The first one is memory growth per request actually, right? When I say memory growth per request, so we are going with a sliding window log. Yep. Sliding window log stores one timestamp per request, right? Under heavy traffic or the long windows, memory can grow large, right? Memory can grow large accordingly with what code that we have written. So this one we have to keep in mind. The second one is single process only. When I say single process only, the particular implementation, whatever we went with, so it enforces limits only for a single process instance. It limits only for a single process instance in multi-instance deployments. So this will not coordinate across the instances. Yeah. In the multi-instance deployments, this will not coordinate across instances. Just keep this in mind. Next, the third one, the important one, lock contention for the hot case. When I say lock contention for the hot case, so just listen to this carefully. If a single key receives very high concurrent traffic, right? So I had showed this one, 3 for the same key, right? In the example we considered. Basically, if a single key receives very high concurrent traffic, then the threads will contend on its lock. The threads will contend on its lock, meaning a possible throughput. So this is the possible throughput bottleneck actually, right? So next, let's go with a no eviction for many keys, meaning no eviction. This one, no removal for or no deletion for the many keys, right? So when I say this, whatever the store and the lock dictionaries that we are making use of in the code, the store and the lock dictionaries, right? So this will grow with the new keys, right? No TTL or the LRU, least recently used cache eviction included here, right? So this is one of the limitations as well. So next, let's move on with the fifth one actually, time precision and the monotonic. When I say time precision and monotonic, so we are making use of time dot monotonic, right? So if you observed in the code, we are just going with a time dot monotonic. So within the two helper methods, actually, we are making use of this one, time dot monotonic actually. So this is good, but clock drift across machines in distributed mode must be considered as well. Must be considered as well. Just remember this one. Yeah. Finally, let's move on with the last one, nothing but the sixth one here. Not hardened for the production. Not hardened for the production in the sense, no metrics, right? No metrics here, no back off or the hysteresis here, no instrumentation or the observability, no persistent storage. Yeah. So this is nothing but it's related to the not hardened for the production. Yep. So these are the limitations, man. These are some of the limitations that I wanted to discuss with you guys. Next, let's move on with the alternative algorithms and the trade-offs. Trade-offs is nothing but the summary part. Yeah. So this is nothing but related to the future discussions. Yeah. So that we have to keep in mind, basically. We have to keep these things in the mind. So first thing I want to discuss here is fixed window center. When I say fixed window center, so basically the mechanism is, so we can maintain a counter per discrete window bucket that we can do. Yeah. When I say, listen to this carefully. We are speaking of the fixed window counter, the first one actually. Yep, the first one. So mechanism here is we have to maintain a counter per discrete window bucket. Yeah. So main advantage of this one is very low memory and CPU, right? And also we can just go with a constant time. Yep. So what is the main con here? Disadvantage of this one is, so it allows bursts at window boundaries, right? So the simple example is hitting the end of the window, then start of next. Actually, this is one of the simple examples. This is one of the biggest con actually. Yep. So this is best for low cost approximate limiting with a burst tolerance. Yeah. So this is fine. Now we can just go with a sliding window counter approximation. So when I say this one sliding window counter, listen to this carefully. What's the mechanism here? We can keep two buckets. One is current and the previous, and we can interpolate count. Yeah. The main advantage is low memory, smoother than the fixed window, the previous one, right? Smoother than the fixed window and approximate correctness. Yeah. Main disadvantage or con of this is slight inaccuracy for the edges, slight inaccuracy for the edges. So this is best for large scale systems that accept small approximation, Yeah. So this is fine, I believe. Next, let's move on with the third one, man. Token bucket. Yeah. Let's move on with the third one, nothing but the token bucket. So when I say token bucket, so it's also known as the leaky bucket, basically. What's the mechanism here? So we can refill the tokens at the steady rate. So if you know the leaky bucket algo or the token bucket algo, we can refill the tokens at the steady rate, right? So it also allows bursts up to the bucket capacity. We have idea on this. And what is the pros and cons here, advantages and the disadvantages? So basically the one of the biggest pros here is it supports smoothing of the burst and rate shaping, right? Rate shaping, nothing but it is efficient. And what's the disadvantage or the con here? So the main con or the disadvantage here is it is slightly more complex, right? So it needs atomic operations in the distributed mode. Yeah? And it is best suited for this one, APIs needing burst allowance with a steady state rate, right? Steady state, right? Steady state rate. Yep. So this is fine, I believe. Next, let's move on with the Redis based approaches, right? This is distribute. We are considering for the distributed ones, right? So this is fine. For the first point here is sorted sets, right? So the main advantage here is this one, sorted set actually. When I say sorted set, so I'm speaking of the Z set. Yeah, I'm speaking of the Z set, right? So we can store the timestamps as scores. So we can just make use of Z rem range by score actually. The red is we can just go with Z rem range by score actually, by score. Yeah, this one. Also, we can just go with the Z card plus Z add. We can just go with the Z card as well as the Z add actually. Z add. Yep. In the Lua script to keep the atomicity. Yep. Next, atomic token bucket with the Lua actually. What happens here? We can just store the tokens and last refill time as well. And also we can compute or calculate refill and decrement this one atomically. So this is one of the advantages as well. Next, one of the pros here is so it is distributed atomic consistent across the instances. Yeah, what's the main con here then? What are the disadvantages here? External dependency, the main thing of using the distributed, right? So external dependency in the sense additional latency. We have to take care of the cost as well, and using the Lua scripting to avoid this one race conditions actually. Yep. So cost I'm speaking of mainly. Yep. So this is fine. Finally, let's come to the fifth one here, hybrid or the approximate techniques. Meaning, so here, one of the simplest examples is rate limiting with Bloom filters or hyper double log, meaning hyper log log. Yeah. So for specific use cases where exact counts are not required, so this is memory efficient, right? Probabilistic structures may be used as well in this case. Yep. So this is one of the things. So final ones, let's go with the trade-off summary here. So let's discuss three things here. One is accuracy versus memory, and another one is single node versus distributed. The final one is simplicity versus features, right? So first one is accuracy versus memory. When I say accuracy versus memory, sliding log is accurate, no doubt. Sliding log, this one, whatever the algorithm that we use to write the code is sliding log, right? So sliding window log actually. Sliding log is accurate, no doubt, but memory heavy, right? Counters or token buckets use less memory but differ in the semantics. Always remember one thing, counters or tokens, this one token buckets use less memory, but it might differ in semantics. So this is it for the accuracy versus memory. Let's come to the second part, which is very important, single node versus distributed, right? So when I say single node versus distributed, just remember one thing, in memory is extremely fast, intensely fast. We know this one. In memory is fast, but it is not global. One of the main disadvantages actually. In memory is fast, but not global, right? Redis or Lua script, whatever we discussed, right? Redis or Lua is consistent, but adds network latency. But it adds the network latency. These things we have to consider under single node versus distributed. Distributed in the sense we have spoken about the we had spoken about this one, Redis or the Lua script, right? So that's related to the distributed. Single node, this one, and we are speaking of the in memory. So single node in memory is fast but not global. Distributed Redis or Lua script is consistent but adds the network latency, right? So we can go with something that's actually helpful for us, right? That's relevant to us, right? Based on the specification. And the final one is simplicity versus features, right? So when I say simplicity versus features, simpler algorithms are easier to implement. No doubt, simpler algorithms are easier to implement and reason about. Advanced algorithms support burst handling, smoothing, and distributed atomicity. In our case, choosing the this one, sliding window log, this one, algo was the best one, right? I found that it was the best one to use, so I have made use of this one, right? So let me finish it off with this. Let me finish it off with this. We have discussed mostly everything, right? Along with the coding and the output part as well, along with the code and the output part. So I hope this completes the this one. Designing a rate limiter completely, right? So we have discussed most of the things that we wanted to, right? So now we are done with the this one, designing a rate limiter, right? So next we'll be discussing on the this one, designing load balancer, right? So for now, this is it. Thanks for watching, guys.